In this video, we'll consider tangent planes and linear approximations of functions of two variables. So just like in the single variable case where you had the tangent line to the graph of a function at a point, we also can talk about the tangent plane to the graph of a function of two variables at a certain point in the domain of the function. So that's what we'll do. So imagine having a function of two variables and some point x0, y0, and what we want to do is come up with an equation for the plane that touches the graph of the function at the point x0, y0, f of x0, y0, so with these three coordinates. So imagine that we have the usual 3D coordinate system with the axes x, y, and z, and let's imagine that the domain of our function is something like this in the xy plane. That's where we have this point with coordinates x0, y0. So the special point above which we have the corresponding point on the graph of the function, which is a surface. So we have that point, let's say up here on the graph of the function, and we want to come up with an equation for the plane that touches the graph of the function exactly at that point. Okay, for that we will use the partial derivatives. So this is the tangent plane. Okay, and we want to obtain an equation describing this plane using the partial derivatives. So what do we need in order to write down the equation of the plane? Well, we need a point on the plane that we already have. So that point right there, as I mentioned, it has coordinates x0, y0, and f of x0, y0. Okay, these are the three coordinates of that point, and we need a normal vector for the plane, so a vector that is perpendicular to the plane. So the way we are going to obtain it, at first we get two vectors that are parallel to the plane, and then we use the cross product to come up with a normal vector. Okay, so what we'll do first is obtain the partial derivatives to see what's the rate of change in the x direction. So this will give us a vector a, and similarly if we vary y and leave x fixed, we get this vector b, and the cross product of those two will give us the normal vector. Okay, but what are these vectors a and b? Well, to get a, what we'll have to do is vary the x variable and keep the y variable fixed. So a vector that does that and gives us the direction, well, as we've learned, the partial derivative with respect to x gives us the slope of the tangent line in the x direction when we cut through the graph of the function with a plane that's parallel to the xz plane, so y is being fixed. And if we do that, we get a curve to which we can draw a tangent line, and that tangent line has a direction vector, and that is this vector a. So if we step one unit in the x direction, the y direction is being fixed, so in that direction we don't move with this vector. So that's why that component is 0. And what's the gain in the z component, in the height that we get? Well, that's exactly the slope in the x direction. So that is given to us by the partial derivative with respect to x at that point x0, y0. So this is our vector a, which gives us a vector that's parallel to the tangent plane. Similarly, in the y direction, if we vary the y component, it means we don't move in the x direction, if we step 1 unit in the y direction, we gain in the height an amount that is given to us by the slope in the y direction. That's the partial derivative with respect to y at that point x naught, y naught. So now that we have these two vectors, we can form their cross product to get a normal vector to the plane. Okay, so if you compute this cross product, what you will find that its components are as follows. It's the x component is minus f of x, f sub x, x naught, y naught. The j component or y component is minus f sub y, x naught, y naught, and the z component is plus 1. So this is the normal vector to the tangent plane. So now we have a point on the plane, that this is this point, and we have now also a tangent, a normal vector, that is. So with these two, now we can go ahead and write down the equation for the plane, which is given by the relation that the normal vector is perpendicular to any vector in the plane. So if I denote the corresponding position vector corresponding to this point r naught, and a general position vector that points to the plane, to some point on the plane with components x, y, and z, x, y, and z, then this relation that the normal vector is perpendicular to any vector in the plane turns into the following. Just imagine, let's just use these formulas. So this is the normal vector. With these three components, we are taking the dot product of that and r minus r naught, which in this case is x minus x naught, y minus y naught, and for the third component we have z minus the z component of r naught, which is f of x naught, y naught, equals, well, this should be equal to 0. So let's spell this out using the coordinate formula for the dot product. So if we just write this out, this is minus f, the x derivative with the partial derivative with respect to x at that point, times x minus x naught, minus the partial derivative with respect to y at that point, times times y minus y naught, and finally we have plus z minus f of x naught, y naught, equals 0. Now we can rearrange this equation to express z as follows. So we add this quantity to both sides to get the partial derivative with respect to x at the point of x naught, y naught, times x minus x naught, plus the partial derivative with respect to y at x naught, y naught, times y minus y naught, and finally plus the function of the value at x naught, y naught. Okay, so this is the equation of the tangent plane at x naught, y naught. So the equation of the tangent plane drawn to the graph of the function f at the point x naught, y naught. Okay, and with that, let's see an example. So my question for you is to consider the function f of x, y equals 2x squared plus y squared. Okay, and let this point given by the position vector r0 have coordinates 1, 1, 3. And find the task is to find the equation to the tangent plane, an equation to the tangent plane to the graph of this function. Okay, pause the video and input your answer below. Okay, I hope you paused it and computed the partial derivatives to be, so f partial derivative with respect to x is 4x, and the partial derivative with respect to y is 2y. So these give you 4 and 2 when evaluated at that point, x0, y0, they are both equal to 1, so give you 4 and 2, which means that this formula turns into the following. So the equation for the tangent plane is going to look as follows. Z equals 4 times x minus 1 plus 2 times y minus 1 plus the value of the function at that point is 3 plus 3, okay, which you can expand to get 4x plus 2y minus 4 minus 2, that's minus 6, plus 3, that's minus 3. So the equation of tangent plane is z equals 4x plus 2y minus 3. So that concludes this example. I hope you enjoyed this video, and I'll see you in the next one.